Hello everyone, welcome to today's class. In this lesson, we are going to study consecutive integers. This topic is very important in math competitions because it connects algebra, number theory, and problem-solving tricks. By the end of today's lesson, you should feel comfortable working with sums of sequences, finding missing numbers, and applying some interesting theorems. Let's start with the basics. Consecutive integers are numbers that come one after another, like 1, 2, 3, 4, and so on. More generally, we can talk about an arithmetic sequence, where each term increases by the same difference. For example, 1, 3, 5, 7 has a difference of 2. 1, 5, 9, 13 has a difference of 4. So consecutive integers are just a special case where the difference is exactly 1. Now, how do we find the sum of an arithmetic sequence? There is a famous formula. The sum equals the first term plus the last term, divided by 2, then multiplied by the number of terms. Let's think about why this works. If the numbers are evenly spaced, the first and last give you the average of the whole list. That's just the mean value. Multiply the mean by how many numbers there are, and you get the total sum. That's the logic. When we work with arithmetic sequences, one very useful question is, how do we figure out the number of terms in the sequence? There's a simple formula for this. The number of terms, usually written as n, is equal to the last term minus the first term, divided by the common difference, and then add 1. So in symbols, it looks like this. N equals last term minus first term, divided by d, plus 1. Let's see how it works in a special case. If the sequence is just consecutive integers, then the common difference d is 1. In that case, the formula becomes even simpler. N equals last minus first plus 1. Let's go through a few examples together. First, if you add all the numbers from 1 up to 20, you're really looking at the sequence 1, 2, 3, and so on, all the way to 20. That's an arithmetic sequence where the first term is 1, the last term is 20, and there are 20 terms in total. The average of the first and the last is 10.5, and if you multiply that by the number of terms, 20, you get 210. So the sum of the numbers from 1 to 20 is 210. Now, let's try the odd numbers from 1 to 15. That sequence is 1, 3, 5, 7, 9, 11, 13, and 15. The difference between terms is 2. The first term is 1, the last term is 15, and there are 8 terms in total. The average of the first and the last is 8, and multiplying by the number of terms, 8, gives 64. So the sum of the odd numbers from 1 to 15 is 64. Finally, let's look at the positive odd multiples of 3 that are less than 100. The sequence goes 3, 9, 15, 21, and so on, until 99. Notice that the difference here is 6, because each term is 6 more than the one before. Now, to find out how many terms there are, we can use a simple formula. Take the last term, subtract the first term, divide by the common difference, and then add 1. So here it's 99 minus 3, that's 96. Divide 96 by 6, you get 16. Then add 1, and that makes 17. So there are 17 terms in this sequence. Once we know the number of terms, we can use the average method. The average of the first and last is 51. Multiply that by 17, and you get 867. So the sum of all the odd multiples of 3 less than 100 is 867. Now let's revisit the middle number method for computing the sum of consecutive integers. The idea is that the sum equals the middle number times the number of terms. If the number of terms is odd, the middle is just the central integer. If the number of terms is even, the middle is the average of the two central numbers. Let's test this method with some problems. Suppose the sum of 3 consecutive integers is 6. Then the middle one is 6 divided by 3, which is 2. Easy. Next, the sum of 4 consecutive integers is 10. Then the average is 10 divided by 4, which is 2.5. That means the two middle numbers are 2 and 3. Another example. The sum of 5 consecutive integers is 30. The middle one is 30 divided by 5, which is 6. So the sequence is centered at 6, and the largest is 8. If the sum of 4 consecutive integers is 22, the average is 5.5, so the two middle terms are 5 and 6, and the sequence is 4, 5, 6, 7. The smallest is 4. Here's a bigger one. The sum of 6 consecutive integers is 2019. The average is 2019 divided by 6, which is 336.5. That means the sequence is 334 through 339, and the largest is 339. Another one. The sum of 101 consecutive integers is 101. The average is 1, so the middle number is 1, and the largest is 51. Finally, suppose the sum from negative 22 to some number x is 98. The sum from negative 22 to 22 cancels out to 0. Then we need to add more terms until we reach 98. If we add 23, 24, 25, and 26, we get exactly 98. So x must be 26. Good. Now let's move into some deeper theorems about expressing numbers as sums of consecutive integers. We are going to look at the sum of k consecutive integers starting from m, and see how we can derive the formula and analyze its properties. The sum can be written as n equals m plus 1 plus m plus 2, and so on, up to m plus k minus 1. Since this is just an arithmetic sequence, we can use the formula for the sum of an arithmetic progression, the number of terms times the sum of the first and last term, divided by 2. Here, the number of terms is k, the first term is m, and the last term is m plus k minus 1. Substituting these in, we get n equals k times m plus k minus 1, all divided by 2. Simplifying, this becomes n equals k times 2m plus k minus 1, over 2. So, after multiplying both sides by 2, we get the key equation. 2n equals k times the expression 2m plus k minus 1. Now, let's think carefully about this term, 2m plus k minus 1. We can look at it as 2m minus 1 plus k. The part 2m minus 1 is always odd, because 2 times any number is even, and if you subtract 1, you end up with an odd number. That means the parity of the whole expression depends entirely on k. If k itself is even, then an odd number plus an even number stays odd. But if k is odd, then odd plus odd makes an even number. In other words, k and the term 2m plus k minus 1 can never share the same parity. Whenever k is odd, the other is even, and whenever k is even, the other one is odd. This ensures that their product is always even, which matches perfectly with the left-hand side, since 2n is of course even. Next, let's consider the size of 2m plus k minus 1 compared to k. Since m is at least 1, we know that 2m plus k minus 1 is greater than or equal to 2 times 1 plus k minus 1, which simplifies to k plus 1. So, in fact, 2m plus k minus 1 is strictly greater than k. At first, this might sound a little abstract, but it becomes really useful when solving problems. Let's try one. Which value of k cannot express 165 as a sum of k consecutive integers? In this case, the sum n is 165. We compute 2n, which is 330, and factor it. The factor pairs are 2 times 165, 3 times 110, 5 times 66, 6 times 55, and so on. For k equals 2, 3, 5, and 6, the conditions work. But for k equals 4, the division gives a fraction, not an integer. So k equals 4 is impossible. That's the answer. Another example. Write 105 as the sum of 10 consecutive integers. The average is 10.5, so the sequence is centered at 10.5, with 5 terms on each side. That gives us 6 through 15. The largest number is 15. Now let's talk about an interesting theorem about products. The theorem says, the product of any k consecutive integers is divisible by k factorial. Why does this hold? Think about combinations. The number of ways to choose k objects from n is n times n minus 1 times n minus 2, all the way down for k factors, divided by k factorial, since order doesn't matter. That formula always gives an integer. So the numerator, which is the product of k consecutive integers, must always contain k factorial as a factor. That's the reasoning. Let's test this idea with a problem. The number n equals n plus 4, times n plus 5, times n plus 6, times n plus 7. This is a product of 4 consecutive integers. According to the theorem, it must be divisible by 4 factorial, which is 24. That means it's automatically divisible by 3, 4, 6, and 24. But is it always divisible by 5? Not necessarily. If n equals 1, then the product includes a 5, so it is divisible by 5. But if n equals 2, then the numbers are 6, 7, 8, 9, which do not include a 5, so the product is not divisible by 5. Therefore, the correct answer is 5. That completes all our examples for this chapter. Let's wrap up. Today we learned how to calculate sums of arithmetic sequences using the mean value method. We studied the middle number trick to quickly find terms from the sum. We discovered the formula to express numbers as sums of consecutive integers, and we explained the important parity condition. Finally, we understood why the product of consecutive integers is divisible by factorial, and we applied that to problems. These are very powerful tools that combine ideas from algebra, number theory, and combinatorics. I encourage you to practice these problems again on your own and make sure you are comfortable with both the reasoning and the calculations. That's all for today's class. Thank you for your attention, and I'll see you in the next lesson.